My name is Jiong from Intel. So I'm the software architect on PyTorch optimization. I'm also one of the PyTorch CPU module maintainers. So I'm very excited to be here today to share the latest improvements that we've made to TorchInductor CPU backend. So unfortunately, my co-author Leslie Fang cannot be here, but the work that I'm going to present today is teamwork from Intel, so I'm very glad to share their great contributions. So I will start with an overview of the TorchInductor CPU backend, its architecture and main features. Then I will share highlights into some new features that we've made into TorchInductor CPU backend since the last year. Finally, I will have a deep dive into these new features. So TorchInductor CPU backend is the default compiler backend for PyTorch CPU. It works in two modes. The just-in-time compilation mode with torch.compile and ahead-of-time compilation mode with torch export and AOTInductor for Python-free deployment. So it operates in two modes. Firstly, it processes the FX graphs, applying the pattern-based graph fusion to map the important deep learning patterns to the CPU A10 kernels. For example, the SDPA that implemented with the flash attention algorithm, and also the weight-only-quantized GEMMs for low-bit LLM inference, and also the conv linear fusion, the epilogue fusion. Then the FX graph are further lowered to the inductor loop level IR, which the code generation module uses to generate code. So there are three code generation backends. The most complete and best performing backend is the CPP OpenMP backend, which generates the CPP code and leverage the OpenMP to do the parallelization. It supports both the static shapes and dynamic shapes. It supports all the commonly used data types in deep learning. It runs on Linux, Windows, Mac, and it supports the explicit vectorization based on the A10vec abstraction. It also supports the Max-autotune mode that to further optimize the GEMMs. So the CPP OpenMP codegen is the focus of my talk today. There are also other two experimental backends that generate highlight and Triton code, which the MetaFocus is working on. So here's a recap of the features I just mentioned. So we use three main benchmarks, TorchBench, Hugging Face, and the TMM models to evaluate the performance and the quality of our software stack. So over time, we've seen the continuous improvement of the quality of a TorchInductor CPU backend. At this point of time, we can see that there's only a few failures from the B416 inference, but in fact, most of these failures are due to the test cases themselves. We are also closely monitoring the community reported issues to make sure that we respond and fix these issues in a timely manner. So we've been continuously improving the performance of the TorchInductor CPU. To demonstrate the steady progress, I'm showing the performance speed up of TorchInductor CPU versus the eager mode, the trend, since the last year, using bflow 16 inference as an example. As we can see, we have achieved significant performance gains across the board with popular data types. So now let me introduce the new features that we've added since last year, some of these new features. Okay? First up is the CPP vectorized codegen. So this is the foundation of the TorchInductor CPU backend. The vectorization relies on the A10vec abstraction, which allows us to generate code to run efficiently on multiple CPU architectures. So in the example on the right-hand side, we can see we have 2D tensor being multiplied by itself, creating a 2-level loop nest. So the code generation analyzes the data access patterns and sees that the data access is contiguous in the innermost dimension and vectorize on it. So we've extended the CPP vectorized codegen to support all the commonly used data types, and also all the inductor IR constructs, including index expressions and masks, etc. We also added other optimizations and optimized the loop schedules. I will share more details in later slides. So the next feature is about Max-autotune, which is used to further improve the GEMM. So Max-autotune is the feature that selects the best performing kernel by profiling various implementations at runtime. So for CPU, the default implementation of GEMM is the A10, powered by 1DN and MKL libraries. So now we've added the CPP GEMM template that optimizes for data reuse, cache locality, instruction selection, register allocation, and more flexible epilogue fusion that further boosts the GEMM performance. So this slide shows the performance speed up with the CPP GEMM template versus the default compilation mode. So as we can see that even though this is just the end-to-end model speed up, not all models are heavy in GEMMs. Still, we can see the speed up are promising, with some models having more than 20% speed up over the default compilation mode, especially for the models, NLP models and the recommendation models, which are heavy in GEMMs. So we all know large language models is having with GEMMs. So we tested the performance with the Torch Chat Llama 3.18 billion bflow 16 inference. So the default compilation mode brings 4x speed up, and the Max-autotune mode brings additional 20% speed up on top of it. Okay, the next big update is the Windows support. So now TorchInductor CPU can run on Windows. So we've added multiple compiler support with various compiler options and language standards, such as Microsoft CPP compiler and Intel CPP compiler. Now both the performance and pass rate are in good shape. So feel free to try it out. Okay, so now let me have a deep dive into the CPP vectorized codegen. I will show you how we vectorize the code and how we optimize the loop schedule. After that, I will also share the internals of a GEMM template. So for vectorization, we tackled two key challenges. Identifying which loop variable to vectorize by analyzing index expressions, and aligning vectorization factors across different data types. So the key to vectorization lies in analyzing the strides of loop variables in these index expressions. So the index expressions show up in the load store operations, and also there are bare index expressions for index arithmetics. So in the simplest case, if the stride in of the loop variable in the index expression is 1, we know that we can vectorize on it, like the first case shows. The expression could also be nonlinear, including floor div and modular indexing, like the second case shows. And also, the expression can involve the variables loaded from other buffers. We call it indirect indexing, like the third case shows. For bare index expressions with constant strides, so we can vectorize the expression using vec range. So for example, in a padding operation where we need to check if an index is out of range, right? So instead of performing scalar checks one by one, we can use a range to vectorize these checks and build a vector mask. So this provides a significant performance boost, in this case, 6 times speed up over the scalar kernel. For indirect indexing, we analyze the data dependencies between the loop variable and indirect indices. So if the loop variable is not depend on the loop variable, we can still vectorize on it. So an example is the embedding lookup, so where we can vectorize on a loop variable that loops over the embedding feature vectors. We achieved 5 times speed up in this case. More complex cases would involve non-linear expressions, including the floor div and the modular indexing that I have introduced. So this index expression arises from the reshape and the slicing operations, etc. So in some cases, we can still simplify these expressions and make the vectorization possible. For example, this particular case appears in the TMM model that after the simplification of index expression, we can vectorize on it and achieved 4 times speed up. So the key idea here is that we transform the nonlinear expression into the linear form, given the loop variable spans over the vectorized range. So another case comes from the group norm, so where a floor div in the expression was reduced by splitting the loop variable. This allows us to vectorize on the kernel and achieve the 2.5 times speed up. So if finally the index expression cannot be simplified, or the indirect indexing depends on the loop variable, so we have to resort to the scalarization, where we gather and scatter the scalar values inside the inner loop. So we try to minimize the scalarization to keep the overall operations vectorized. So when the scalarization becomes too frequent, it might hurt performance. So in this case, we fall back to scalar kernels with some heuristics to avoid unnecessary slowdowns. Vectorization factor is the number of elements a vector kernel processes simultaneously in a single vector operation. So for example, AVX512 can process 16 float elements and 32 before 16 elements per vector. So a vectorized kernel chooses to use a single vectorization factor. So to align the vectorization factor among different data types, a naive approach is to pick the smallest vectorization factor, 16 for float, and then only half of the lanes for before 16. So this wastes the potential of a wider vector lanes. In order to optimize this, we introduced the vectorized N abstraction. So instead of using only half of the lanes, we used the full lanes and we pack 2 float into a single vector to match the 32 elements of before 16. So this can brings, on average, up to 5% speed up model-wise. Okay, so in addition to vectorization, let me introduce a little bit about the loop optimization we've introduced. So we optimize the loop schedule by fusing the outer loop of multiple kernels. So here is a good example how we optimize SoftMax operation, which is a very popular in the deep learning models. So here we fuse 3 kernels from the SoftMax, which helps to reduce the size of intermediate buffers and improve the cache locality. So this brings 10 times speed up. So after introduced the vectorized codegen that all the optimizations, now let's take a closer look at the GEMM template. So the template operates on 2 levels of abstractions. So at the top level, there are outer loops, which can be shared by multiple CPU architectures. So we perform thread blocking, where we split M, N, and K dimensions into smaller block, MT, NT, and KT, in order to maximize thread occupancy. Then these blocks are further split into cache blocks, where the blocks are further divided into MC, NC, and KC, which are optimized for L1 and L2 cache use. So once the thread and the cache blocking is done, the template invokes the next level, which is the micro-GEMM template. So it is CPU architecture specific and the performance register blocking, which map the blocks to CPU registers. And finally, we generate the epilogue fusion, for example, the linearity and the bias, the residue add operation, and we at the cache level, so that they can compute at the same time in the inner loop to get a further speed up. So we reuse the CPP vectorized codegen to generate these epilogue fusion. So the micro-GEMM template handles small gems, with the register blocking and instruction selection, optimized for data types and the CPU architectures. So for example, on the 4th generation Xeon processor, we allocate 8 tile registers for A, B, and C, and use the tile dot product to compute the gems based on the advanced matrix extension instructions available in the processor. So if the processor only supports the AVX512 instructions, we use FMA to compute the dot product. To maximize cache reuse, we block B into small L1 size tiles, which are reused by L2 size tiles of A. Then subsequently, the L2 size of tiles of A are further reused by multiple tiles of B. So for inference, we also prepack B to make data access contiguous within these tiles. So all these optimizations help boost the GEMM performance. Okay, looking forward. As the inductor CPU backend matures, we are moving forward to make it a stable feature. We are also working on to harden the Max-autotune feature for more performance gains in GEMMs. And of course, we welcome contributions from the community to expand the support for more CPU architectures. So finally, I'd like to express thanks to Jason Ansel, Bin Bao, Horace Kerr, and other Meta colleagues for their guidance and the review of our contributions. I'd also like to thank Renat and Ye from Intel, who shared their insights in GEMM algorithms, and which significantly influenced our optimization in GEMM template. So it's been a very exciting journey to work on inductor CPU backend, but I don't think it's possible without the support from a wider PyTorch community. So thank you all for all the great help and the contributions. Thank you.